So in this question, we're asked to write a second-order ODE as a system of two first-order ODEs, and then solve the system using the eigenvalue and eigenvector approach if we're given these particular initial conditions. So the process that we're going to go through, I've summarized in a series of 5 steps. So we're going to start by modeling the system in the form y dash is equal to y times a, which is a matrix equation. We should be able to draw that matrix A into the next step and use it to solve for eigenvalues, which must satisfy this equation here. Once we've got the eigenvalues, we should be able to solve for the eigenvectors using this particular equation. We then write out our final solution and solve for the constants k1 and k2 using the initial conditions. So just be aware that all of the quantities in here which are bolded that you see, these are not scalars. They are bolded because they're vectors. Alright, so moving back over here. So we're going to start by rewriting this second order equation as two first order ones. So how we're going to do that is we're going to introduce a new variable, and you can call it whatever you want, but I might call it z, and we're going to let it equal to be the first derivative of what was used up here in the equation, so it's going to be w dash. What we're going to do now is substitute this equation back up in here, and we should be able to rewrite the equation as a first order then. So the second derivative of w can be rewritten using this as the first derivative of z, since one of the derivatives is already wrapped up here. Then we can write plus 10, and we can replace w dash with the z that we introduced. And there's not much we can do here, so we just leave it as minus 3w is equal to 0. So what we can see now is that this one equation has been rewritten in terms of these two other first order ODE systems, okay, because the highest derivative in both of them is a first derivative. So now the challenge becomes writing it in a matrix equation. So we saw a moment ago that it needed to look like this. I've put the underbars on to represent these as vector quantities when I write it out by hand. So what we want is on one side of the equation, the derivative terms. So I could rewrite this one here as being w dash on the left equals z on the right. So that's one equation that's kind of written in this notation. And I'm going to swing these two terms to the other side so we just get the z dash on its own here. So we can rewrite this as 3w minus 10z. Alright, so now let's come across and try and write it with the matrix equation. So this left-hand side is going to be the w dash and the z dash, and they're going to be two elements of the vector, of the matrix. A is going to be a 2 by 2 matrix that we'll fill in a moment, and then y over here, right, I'm going to put it in the same order as what we have here, so w and z, right, but they're not the derivatives, okay? So now what we need to do is fill out what's in the A matrix. So remember for the matrix multiplication, this element here is going to be equal to the first element of A times by W plus the second element here multiplied by Z. So if we look back up at the equation that we're trying to write into the matrix, we've got the W dash, which is good. So we need it to equal Z on the other side. So this element gets multiplied by w, and it's going to have to be a 0, so it kind of drops out of the equation. And then the second element here is going to have to be a 1, right, because then it's 1 times z, which leaves me with z. So I've satisfied then this equation with that calculation. If we then look at this second one here, z dash, right, we need to program this equation. So the number here gets multiplied by w, and we're going to want that to be a 3. And then the number here gets multiplied by z, and we're going to want that to be negative 10. So this here is the matrix version of these two simultaneous equations. Right, so that completes pretty much step 1 of our process. So step 2 over here was to look for the eigenvalues, which is the lambda in the equation, and we can see we need to satisfy the determinant of a minus lambda times I is equal to 0. So let me pop that down here. So the determinant of this is equal to 0. So let's have a sub-step where we figure out what a minus lambda I actually is. So A is the matrix that we just developed a moment ago. So the 0, 1, 3, negative 10. Lambda is the eigenvalues that we're going to try and get out. So we'll just leave it like that. And I is the identity matrix that fits. So since this is a 2 by 2, we want the 2 by 2 identity. Remember, identity matrices have 1s down the main diagonal and 0 everywhere else. So I'll copy this across, and then let's put lambda into the matrix. So we're going to get lambdas down the main diagonal and 0s everywhere else. And we'll actually now do the takeaway step. So 0 minus lambda leaves us with negative lambda. 1 minus 0 leaves us with 1. 3 minus 0 leaves us with 3. And negative 10 minus lambda is the last element. Alright, so the determinant of this has to be equal to 0. So the determinant of a 2 by 2 matrix is like the AD minus BC rule. So we get negative lambda, negative 10 take lambda, multiplied together, minus 1 times 3 has to be equal to 0. So if we expand this out, we're going to get this. And if I rewrite it to have the highest powers down to the lowest powers of lambda, we get that. You can see that this is a quadratic equation. So we're going to need to solve it using the quadratic formula. So the number at the front of the squared term is a 1, the number at the front here is 10, and the constant on the end is negative 3. So applying the quadratic formula, which looks like this, we should be able to sub our values into it. And this simplifies down to be 112 over 2, and we're going to get two answers out for lambda. So the first one is going to be, say we take the plus version of this, and if you type that into a calculator, it's approximately 0.292. And then if we take the other version, so the negative 10 minus square root of 11212, this one works out to approximately negative 10.29. So what we've just found here are the two eigenvalues for our solution. Alright, so we're now up to the next step of our process, and that was to solve for the eigenvectors. So that's the C vector that we see here. So we need to satisfy this particular equation. Step 3, so the equation that we were satisfying was a minus lambda I times the C vector is equal to the 0 vector. And I'm going to start by doing this for the first lambda value that we found, so 0.292. So if I write out this equation for this one here, putting in my subscripts, so we've got lambda 1, alright, and I'm going to call this C1 for the first. This is the eigenvector that we're looking for. Okay, so this one here is kind of like a matrix, and we already simplified that somewhat back up before. So A minus lambda I is going to be equal to this. So we just need to substitute in our lambda value that we're considering. So if we do that, we're going to get negative 0.292 in this first one, 1, 3, and this becomes that. It's multiplied by the eigenvector C1, and I'm going to write it out as an actual vector. So you can call the elements whatever you want, but I'm going to call them C1 and C2, and these are scalar values, so just numbers. And this is the 0 vector on the end. So if you do this matrix multiplication, it's going to end up needing to be a 2-row, 1-column matrix, and everything in it is 0, since it's the 0 matrix, or 0 vector. Alright, so since this first part here, alright, we had a condition on it before where the determinant of it was equal to 0. So as a result of that, we know when a determinant is 0 of a matrix, it means that there's a row that is a multiple of another row. Okay, and since we only have 2 rows, that means that both of them are multiples of each other. So whether we read out the equation corresponding to the first row or the second row, they're going to be essentially the same equation, or they can be cancelled down to look like the same equation. So it doesn't matter which one you pick. I am going to pick the top one. So we can write this as 0.292 multiplied by the C1 that we see there, plus this next element gets multiplied by C2 for the row by column calculation, and we know it's equal to the first element up here, which is 0. So now what I'm going to try and do is rewrite one of these constants in terms of the other one, and the easiest way to do that is to just get C2 on its own, because it's already multiplied by 1, and we get that by swinging this other bit to the other side of the equation, so it becomes 0.292 C1. So this is the relationship that must exist between those two different constants. I said a moment ago that we could write our C1 vector as being equal to this constant C1 and C2. And C1, I'm just going to leave it, but C2 we can replace as being 0.292 C1. What we need to do now is pick a value, any value except for 0, to let C1 be equal to, and then we're going to have a vector that we can substitute into our equation in the moment. So I'm going to write this as let C1, I'm going to make it equal to 1 because that's pretty much the easiest thing you can do. So C1 is 1 and this gets multiplied by 1, so it just becomes 0.292. So just as a reminder, you can literally pick anything except for 0 for this to be equal to. Whatever you get out, it's going to be fine, because in a moment when we move on to the next step, we're going to end up with this K1 value being multiplied by that C1 vector that you had. So the product of these two is going to equal the same amount in the end. So whatever you set C1 to equal at this intermediate stage, isn't going to matter. Alright, so what we need to do is go through this process again to get the second eigenvector out, which is going to be the C2 that forms our general solution. So in order to do that, we go through exactly the same process as what we did a moment ago. So for our second eigen value, so that was the negative 10.29. We need to write out this equation with our lambda and our c appropriately subscripted. So that's going to be a minus lambda 2 times I multiplied by the second eigenvector has to be equal to the 0 vector. So again, we had a version of this that was already simplified. So if we substitute our new lambda value into that, so it's 10.2913 and negative 10 plus 10.29 multiplied by the C2 vector, and again we can call these elements whatever we want. I'm going to call them C1 and C2, and the 0 vector on the other side is going to be just 0 and 0 again. So same kind of deal where you can read out either row, they're going to be the same equation because the determinant of this was equal to 0. I'm going to pick out the first one again. So that means 10.29 multiplied by C1 plus the 1 here times by C2. Alright, has to equal the 0 up on the top there. We want a relationship between the C1 and C2 constants, and the easiest way to get that is going to be swinging this to the other side of the equation. So it becomes negative 10.29 times C1. So we want to write out our eigenvector, okay, this one here, which we've said is constructed from these two elements, C1 and C2. C1 I'm leaving, but C2 I can rewrite in terms of C1. And then it's up to me to pick any value of C1 other than 0 to substitute in. And the easiest one to pick is going to be 1. So if we pop that in, we're going to get 1 and negative 10.29. Alright, so what we've been able to achieve is our two eigen vectors now. So it's going to be this one here and this one here. These are the two eigen vectors. Alrighty. So now what we've got to do is move on to the next step, which is forming our general solution. So up here, the general solution can be written as this, where y is the same as the y we had up here before. Alright, and if we recall back, it was a vector which had w in the top, z underneath. And c1 and c2 in here are going to be the eigenvectors, and lambda 1 and lambda 2 are eigenvalues. So let's draw them down, and then we're going to use our use our initial conditions to solve for the constants. So here we go. So step 4. So we know that the general solution is y equals k1 c1 vector e to the lambda 1 t plus k2 c2 vector e to the lambda 2t. So we can substitute in, we said a moment ago this was w and z. K1 is just a scalar constant that sits out the front. C1 we can replace, that was one of our eigenvectors, so the 1 and 0.292. And lambda 1, this one was equal to 0.292t. Alright, following the pattern through, C2 we just worked out a moment ago, so we can sub that in. And lambda 2 was the negative 10.29. So if we want to, we can actually separate out the two equations, and rather than writing them as like a matrix equation, we can just write them as regular equations. So let's do that. If I draw out the w equation, it's going to be taking everything that's on the top element. So w is equal to the k1 times the top element, which is 1, times the e to the 0.292t, plus the k2 times the top element, times the e on the end. So we could write this a little bit nicer as this. And then let's do the same thing for the z equation. So it's going to be taking everything that's on the bottom. So I might just copy this one out in the nice order this time. So it's 0.292 times k1 times the e, plus we've got this, so negative 10.29 k2 e to the negative 10.29 t. So I'll just highlight these. And hopefully what you see is that we've ended up with this constant times by another constant k1. So that's why it didn't really matter what we picked up here for the c1 value that we selected. Okay, if we had have picked some other value, it would have been okay, because essentially this product is going to have to be equal to a constant value, right? But what combination in here doesn't really matter. Okay, it's just that final product that does matter. Alright, so we're up to the last step, which was solving for the k1 and k2 constants based on the initial conditions. So we were given them way back up at the beginning. Here we go. So the condition is w at 0 is equal to 1 and w dash at 0 is equal to 2. So if we copy those back down, we've got that. I might start by using this first condition here, and it's in terms of w, so that's going to need to go into this equation here. So I'll label them, and we'll start by applying the first equation. So w is being set to 1, and it's wherever t is equal to 0 that's being subbed in. So this is going to end up being e to the 0 and e to the 0 again up here. So we know anything to the power of 0 is 1. So we end up with this. Alright, so you can see we've ended up with the two unknowns appearing in the equation. So we're going to need our second condition to get a second equation, and then we can solve them simultaneously. So in order to set up for that, I'm going to rearrange this equation. I'm going to get it for k1. So swinging this to the other side, it would be 1 minus k2. So now let's go ahead and use the second condition, we can see that it's in terms of the first derivative of w. And if you remember back up way at the beginning, we said that the first derivative was equal to z. So what that means is we can directly substitute this as being z of 0 is equal to 2 into the z version of the equation. So let's go ahead and do that. So 2 is going to be set to z, and then t is 0. Like that. So again, we've got e's to the zeros, which are going to drop out, and we can write our equation a little bit nicer. So now we have two equations with the same two unknowns, so it's just a matter of solving them together. So if I sub k1 into this equation here, I get this. And if you expand out the brackets and move everything with k2 to one side, everything to the other on the other side, it becomes this. And k2 on its own is negative 0.161 approximately. And then you can go back and solve for k1 by subbing it back into the other equation. And it becomes 1.161 for the other constant. So now that we have the two constants, it's just a matter of going and substituting them back into the general solutions up here. Alright, so you can either pop it into these two, or you can pop it into here. Alright, these are the equivalent kind of expressions to each other. So I might pop it in this one here. So we're going to get w is equal to 1.616, multiplied by e to the that minus the other one, e to the negative 10.290. And then if you substitute into the z equation, this one you're going to need to do a little bit of multiplication on the calculator. We get this. So this simplifies down to 0.339, 292t. And this bit is 1.661 approximately. Just to emphasize once again, these are the products that I was talking about are going to end up being a constant value. That will be the same no matter what values you pick back up at this stage for C1. Okay, regardless of these selections, the final answer should end up being exactly the same equations. So this here are the two solutions to the system of equations, and I guess W was what the original equation was written in, so this would be the solution to that second order one as well. So that's all there is for this video, and in another one I will show you how you could verify this using MATLAB.